Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and in this video we are going to solve a gate question. So this question was asked in the year 2009 for 2 marks. So let's read this question. So the question goes like this. In the following process state transition diagram, so we have a diagram here that is a process state diagram. Then the question says that in this diagram, for a uniprocessor system, which means that there is a single CPU in this system, assume that there are always some processes in the ready state. Okay. Now consider the following statements. So we have a few statements here regarding the process state diagram of a system with a one single processor, right? And it also says that there are some processes always in the ready state. Fine. So the question is which of the above statements are true, right? And then you have some options. So there are a few options. So let us go over these statements one by one and verify whether they are true and not, right? So we start with the first statement. What does this statement say? If a process makes a transition D, so here we have the transition D from running to terminated state. Then what does it say? It would result in another process making transition A immediately. So the transition A is between start to ready and transition D is between running to terminated, right? So the statement is basically saying that if a process which is executing instructions it is running comes to a halt, that is it terminates, right? Or it finishes, that is it makes a transition D, then immediately another process will make a transition from start to ready. So let's dig deeper into this. So what happens when a process which is running, it terminates? When it terminates, that control is transferred to the operating system. And now the CPU is basically free. Obviously, the operating system is running on the CPU, but after this, some process has to run, right? So there is a single CPU on which a process just finished and the control was transferred to the operating system. So the next thing that the operating system will do, it will take a ready process, right? So we already had that statement, right? This is a system where there are always some processes which are in ready state, right? So whenever a process terminates and the control is transferred to the operating system, then in that case the operating system will pick a process which is ready to execute and then schedule it on the CPU so that it starts executing. A new process begins execution, right? Once a process finishes execution, the operating system will try to give another process the control of the CPU. So when that happens, then transition B will happen, that is from ready to running. So we can say whenever transition D happens, then transition B will happen, since we are sure that in this system there is always some process available in ready state, right? So basically D, transition D implies transition B but not A. So let's talk a bit about transition A. When does this happen? So when a new process is being created, right, then it goes from start to ready state. And here a new process is not being created. An old process is just finishing its execution. So this statement is false. That is, transition D does not imply A, because when a process finishes, there is no new process being created. But there are several processes that are there in ready state which can be scheduled on the CPU. So the first statement is false, right? Then let's go over to the next statement. The next statement says that a process P2 in block state, that is this one, can make transition E. So transition E is this one from block to ready, while another process P1 is in running state. Okay. So we are now talking about this transition E. So the question is saying that let's say there is a process which is executing its instruction, it is in the running state. Can any other process which is in the block state make a transition to the ready state? Well, this statement is true. Why? Because the process which is in the block state, why is it in the block state? First of all, it is in the block state because it is waiting for some event to happen, and this event, let's say it is waiting for an IO operation to finish, right? So this has no correlation with the process which is running. An IO operation can complete, and when it completes, the operating system will put the process which is in the block state into the ready state. So let me explain you this in more detail, right? So let's say the process is running, and in parallel there is an IO operation going on for which another process is blocked. So IO operation is taking place on the IO devices, this process is running on the CPU. So these two can go in parallel and the IO operation can finish, and this has no correlation with the process which is executing on the CPU. And when that IO operation finishes, it will notify the operating system. So for a while, the process which is running, it will be paused. The operating system will come into the picture and it will handle that I operation which is just finished. And what it will do, it will unblock that process which was waiting for the I operation to complete. Now the I operation has completed and the unblock process has been, sorry, the block process has been unblocked, right? So like this is completely true that a process P2 which is in the block state can make transition E while another process P1 is in the running state. So this is a true statement. Now next two statements are about preemptive scheduling. So the third statement says that the operating system uses preemptive scheduling. The fourth statement says that the operating system uses non-preemptive scheduling, right? So we just have to figure out whether this process state diagram is for a preemptive scheduler or a non-preemptive scheduler, right? So although we haven't formally talked about non-preemptive scheduler, I have discussed about it in another gate question video, right? I have attached the link in this video also. So let me just talk about what is a preemptive scheduler again here in brief. So we know that what is CPU scheduling? CPU scheduling is the operating system deciding which process should be assigned the control of the CPU next, and then dispatching that process or scheduling that process to the CPU, right? Basically, the operating system is managing who will get the control of the CPU. That's it, right? And here, if you see in this process state diagram, before that, what is a preemptive scheduler? If the operating system, while doing this CPU scheduling, follows a policy where it can take away the control of the CPU forcefully from the running process, right? Here, the word forcefully is important. Let's say a process is running, right? It is executing instructions. Can the operating system forcefully take away the control of the CPU from the running process? This process is called as, this procedure, I'll say, to not confuse between process, right? This procedure of taking away the, this action of taking away the control of the CPU from the running process is known as preemption. We can say that the process was preempted from the CPU. The control of the CPU was taken away forcefully from the process. So can the operating system do it? Is it allowed to do it? If it is, then that kind of scheduling is called preemptive scheduling. And if this is not allowed, that is, if a process is running, then the operating system is not allowed to take away the control of the CPU forcefully from the running process, then it is called a non-preemptive scheduler. Okay, so as you can see in this diagram, there is a transition from running to ready. So this transition signifies that it is a preemptive scheduler. A process can be in running state and it can be like the control of the CPU can be taken away from it, and when that happens, that running process will go to the ready state. Okay, so this transition is a very important one. If this is present, then you can say that this is a preemptive scheduler. If this is absent, then you can see that the control of the CPU will not be taken forcefully. Only when the running process voluntarily relinquishes the control of the CPU, then only control of the CPU can be taken away, will be given relinquished by the process on its own. So what I'm trying to say, if it's a non-preemptive scheduling policy, then this transition will be absent. So there are only two cases when the control of the CPU will be given to the operating system. Once, if it is terminating, that is, it no longer wants to execute, or if it initiates an I operation, that is, it goes into a block state. In this case also, it will give up the control of the CPU to the operating system. In any case here, in case of non-preemptive scheduling, the process is voluntarily giving the control of the CPU to the operating system. No one can take it forcefully as in the case of preemptive scheduling. So this transition state diagram is a preemptive one. So the operating system uses a preemptive scheduling. This third statement is true and the fourth one is false. So we have figured out all the correct statements. So the correct option here is, which of the above statements are true? 2 and 3. The second one is true, that a block process can go to the ready state, right, when a process is running. And the third statement which says that this is a preemptive scheduler. So these two statements are correct. So option C is the right answer. Okay, so guys, this was it for this video. Thank you very much for watching and I'll see you in the next video. Thank you.